In the last couple of videos, we've started to develop a qualitative feel for how the electric force works, and now we want to get more quantitative with it. We will start with Coulombs Law. Coulomb observed that if you have two charges that are interacting with each other, let's say Q1 and Q2, the usual symbol for electric charge is Q. If, say, they're both positive, the forces will repel. The charges will repel each other. So the forces will point away from each other. So just for the giggles here, as a quick pause and ponder, let's just say for the moment that Q2 is 4 times Q1. Which is bigger, the force of charge 1 on charge 2, the force of charge 2 on charge 1, or are they tied? So pause, think about that, and we'll get back together. Okay, so I hope that we agree that they have to be equal to each other via Newton's third law. Newton's third law is still true, so F12 will still equal minus F2 on 1. And remember, this minus sign just means that the vector points in the opposite direction. Oops. And this would also be the case if our charges were both negative. They would still, again, repel, and again, they would be equal and opposite. Now, if the charges had opposite signs, so if one was positive and one was negative, then what will happen is they will attract each other. And again, they will be equal and opposite to each other. The usual way that we give Coulomb's law, we usually write it 2 different ways. For now, we're just going to write in magnitude and say that the force is equal to this big constant K, the Coulomb constant. We'll get to that in just a second. Absolute value Q1, absolute value Q2 over R squared, where R is the distance between the two charges. And well, for the moment, we'll just handle directions by using our common sense and remembering that like charges repel and opposite charges attract. For reasons that will make more sense in a few videos, we also will write this Coulomb constant as 1 over 4 pi epsilon naught. And again, Q1, Q2 over R squared. And you'll probably see me write these equally often. So again, this letter here is a lowercase Greek epsilon. So if you remember the special paper that we all tended to use in, say, 2nd grade, you would write an epsilon. That's a horrible epsilon. You would write an epsilon something like that, or equally acceptable is to write it something like that. Oops. Come on. There we go. So this Coulomb constant is equal to approximately 8.99 times 10 to the 9 Newton meters squared per Coulomb squared. And honestly, you can just go ahead and call it 9 times 10 to the 9 unless you're being very, very fussy. This will be an error of less than 1%. If we write it as this 1 over 4 pi epsilon naught, this epsilon naught gets the name the electric permittivity of free space. And it is equal to 8.85418788128 times 10 to the negative 12 Coulomb squared per Newton meter squared. Now, a lot of books will tell you that that this is an exact number that is not any longer true. With the redefinition of SI that occurred in May of 2019, epsilon naught ceased being an exact number and is now an experimentally measured number, although you can see that it is measured very, very precisely. And again, there, for anything that you're ever going to practically do, you would just say 8.85 or something like that would be probably plenty good enough. All right, so I want you to focus for just a moment on the form of this force law. Have you seen any other law for any other force that has a similar mathematical form? Go ahead and pause for a moment on that, and we'll get back together on that. Okay, so it is very similar to gravity. Remember that the gravitational force is given by big G m1 m2 over r squared. So again, they are inverse square laws that go directly as the charges. In this case, the gravitational charge, if you will, is this inertial mass. Sorry, the gravitational mass, not the inertial mass. The inertial mass is the m in F equals ma. The two numbers have been experimentally demonstrated to be the same two, better than a part per billion. And it could be even better than that. That's just as good as the experiment could get. So it might be worthwhile to just kind of do a quick comparison of the gravitational and the electric forces just to get some sense of it. So let's say I have two 1 kilogram objects that are separated by a distance of 1 meter. And let's also say that they carry a microcoulomb of charge. Let's go ahead and compare the gravitational attraction to the electric repulsion. And spoiler alert here, the force of gravity is going to be a lot weaker. Again, we know these will be equal via Newton's third law. And let's also draw in our electric forces. If we have to clarify what kind of a force we're talking about, we usually write F sub E for electric. And again, that will be an action-reaction pair as well. So let's just go ahead and compute the values, see what we get. So the force of gravity will be equal to G m1 m2 over r squared. So this will be 6.67 times 10 to the negative 11 Newton meters squared per kilogram squared times 1 kilogram times 1 kilogram over 1 meter squared. All right, so that's just a bunch of ones, and we get 6.67 times 10 to the negative 11 newtons for the force of gravity. Now let's do our microcoulombs of charge, which microcoulomb is a decent sized charge, but still this would be K Q1 Q2 over r squared. So this would be 9 times 10 to the 9 Newton meters squared per coulomb squared times 1 coulomb, 10 to the negative 6 coulombs times 10 to the negative 6 coulombs over 1 meter squared. And we get 9 times 10 to the negative 3 negative 3 newtons. So what we get is that the electric force here is 100 million times stronger than the gravitational force. So if I even made the gravitational force vectors 1 pixel long on your screen, even if you're watching this in 4K, I wouldn't be able to begin to fit the electric field vectors onto the screen. So as a practical issue, unless you're dealing with relatively small charges and simultaneously relatively large masses, think planets or something like that involved, most of the time we can get away with neglecting the gravitational force if the electric force is present. It just doesn't show up. I mean, it shows up, but it's basically not even a rounding error. Okay, so where I would like to finish this video up with is taking a look at another property of the electric force, and that is superposition. Now, superposition in physics means that if there's some sort of interaction happening due to multiple players, you can look at each interaction in turn, and then the total interaction just turns out to be the sum of all of them. So as an example here, let's say I stick a negative charge here. Let's say this is -1 microcoulomb. And here I'll stick a positive charge. Let's say this is Q2 equals +2 microcoulombs. Let's say the separation here is 3 centimeters. And then let's go and say that our charge of interest here, Q3, which will make +3 microcoulombs, let's say it's 4 centimeters away. So zoiks, I made this a 3, 4, 5 right triangle. So this distance here will be 5 centimeters. So we'll call this distance here R13. We'll call this distance here R23. So we'd like to find the net electric force acting on Q3. So what our recipe is first what we can do is we can just mentally delete charge Q2. And we can pretend that charges Q1 and Q3 are the only two charges in the universe. And we can say, looking at Q3, oh, it's going to be attracted by Q1. So the force of 1 on 3 will be straight to the left towards this charge because it's attractive. We then pretend that charge Q1 doesn't exist, and that we can pretend that Q2 and Q3 are the only two charges in the universe. And we can see, since they're like charges, they're going to repel. So this would be the force of charge 2 on charge 3 would be something like that. To then get the net effect, what we do is we just add the two forces together as vectors. So let's transfer these forces onto a free body diagram. So we'll draw a dot here for my system, which is Q3. Whoops. And then we'll just go ahead and draw in our force arrows. So this is my F13. That is my F23, like that. And we're going to need to note this angle here. We'll call it theta, which is also, if we were to draw out this triangle right here, that's also this angle theta right there. Now this angle theta is just a shade under 37 degrees. It's 36.9 degrees. It's the interior angle of a 3, 4, 5 right triangle. But let's just call it theta, just so we can kind of review our trig to figure out how to work out the sines and cosines anyway. So to get the net force, we're going to have to add the two forces together. Graphically, you could do that either by the tail to head rule, or I'm going to choose to do it by the parallelogram rule. So by the parallelogram rule, what we're going to get, if you're really good with your art here, is the force is going to be pointing mostly up and just a tiny little bit to the right. And what we want to find is the magnitude of this. We won't get ourselves stressed out about the direction. All right, so to do this, it'll probably be easiest to break this up into, we'll first write expressions for F13 and F23. So F13 will be, oops, no vector here. Just the magnitude will be equal to K times the magnitude of Q1, Q3 over R13 squared. And similarly for F23 would be K Q2 Q3 over R23 squared. And again, we're doing absolute value of the charges because we're just taking care of the directions by hand. All right, so we're going to have to find the x and the y components of my F23 here. So this will be F23y. That's going to be F23x right there. So this is the adjacent, that's the hypotenuse. That's going to give me a cosine. So F23x will be equal to F23 cosine theta, and then similarly F23y will be F23 sine theta. So now we can go ahead and do our vector sum here. We can say that the x component of the net force will be equal to F23x minus F13. And the reason we say minus F13 is F13 is already acting purely along x, and it's pointing to the left, so that's why it gets the minus sign. So we can go ahead and substitute in our expressions for this and simplify. So F23x is going to be K Q2 Q3 over R23 squared cosine theta minus K Q1 Q3 over R13 squared. All right, and we can maybe clean that up just a titch. We can pull out a K and a Q3 from both terms. And be left with Q2 over R23 squared cosine theta minus Q1 over R13 squared. All right, and we can go ahead and start to put in our values. So for K, we'll just use 9 times 10 to the 9 Newton meters squared. Oops, 10 to the 9 Newton meters squared per Coulomb squared. For our Q3, remember that was 3 microcoulombs, so a microcoulomb means 10 to the negative 6 coulombs. Q2 will be 2 microcoulombs, so 2 times 10 to the minus 6 coulombs over our R23 was this distance right here, 5 centimeters. We're going to have to get that into meters, so 0.05 meters squared. And I'm going to have to cheat a little bit here because I'm running out of space. There we go. Now for this cosine theta business right here, we remember that we worked out that this angle theta here is also this angle theta here. And so we can just say the cosine of something is the, by SOHCAHTOA, is the adjacent over the hypotenuse. So that's 4 centimeters over 5 centimeters, or 4/5. So the cosine of my angle is 4/5. Minus my Q1 in absolute value is 1 times 10 to the negative 6 coulombs over 0.04 meters squared. All right, if you punch all that through on your calculator, you'll get 0.405 newtons. All right, cool. Now for the y component, let's go back and look at our free body diagram. In our free body diagram here, we see that only F2 on 3 has a y component. So we can just write that as F2 on 3, which is K Q2 Q3 over R23 squared times sine of theta. So we can just go ahead and plug and grind it. We will have 9 times 10 to the 9 Newton meters squared per Coulomb squared. Q2 we said was 2 times 10 to the negative 6 coulombs. Absolute value of Q3 was 3 times 10 to the negative 6 coulombs. This will be over 0.05 meters squared. And then for my sine of theta, I go back and look here. Sine is opposite SOHCAHTOA, opposite over hypotenuse. So that's 3 centimeters over 5 centimeters. So that'll give me 3/5. So we'll just say times 3/5. And that turns out to be 12.96 newtons. So then to get my net force, I'll need to combine the components with by the Pythagorean theorem. So F net will be equal to the square root of F net x squared plus F net y squared. Take the square root. So this will be the square root of 0.405 newtons. This turns out that this piece basically doesn't matter. Plus 12.96 newtons squared. Take the square root, you get 13 newtons. Alrighty. So in the next video, we will do a very quick introduction to electric fields. Have a good one.